Hey there guys, can you hear me? Please send me hello if you can hear me. I'm starting the talk, the broadcast a minute before the time. And the idea is that I'm doing this because some people come, they are waiting, and then they switch windows, they close YouTube, and then by the time they come back, oh sorry, shit, I missed the time. And then you lose like 10 minutes of the broadcast. So I'm starting this a bit before for the people that were already here waiting. So let me start introducing myself. My name is Leonardo Bezerra. So if you look for me in GitHub, you can find me as Leo Bezerra. Okay, I'm a researcher, developer, and professor. Used to be in that order. I think I should change the caption here. I'm a professor in Natal, in Brazil. The university is Universidade Federal do Rio Grande do Norte, which is basically the state university here, but it's from the federal government, so it's maintained by the federal government. And I'm in an institute called Metrópole Digital, which translates as Digital Metropolis. Okay, so here I teach basically two sets of courses, and they're represented here by these, which are the most relevant of the repositories I have here for these kind of purposes, which are for data science and machine learning, Panda Zero. I'm running broadcasts on Tuesdays at the same time. For data science, the focus is on people who don't program. So this is interesting because you don't know how to code and you're learning to use Python and Pandas. The idea here is this: I could teach you about data science just using graphical interface applications, and I've done that. It's super interesting. But what I figured out is that many people, once they learn that, they want to dive into the command line interface versions, and I would like to give you the opportunity to do that. Okay, so I think I might have been. Okay, I thought I was having internet issues here. If you experience internet problems, you let me know. Okay, so the idea is that Panda Zero is for people who are learning machine data science and they don't code. It uses Pandas, which is probably the most widely used data science library in the Python community, which is by its turn, I think, one of the biggest communities in machine learning, in data science that we have, also for machine learning. And on today, like on Thursdays, I'm hosting this broadcast on scikit-0, which is this repository here. And scikit-0 is for learning scikit-learn, which is probably the best used machine learning library in the Python community. Okay, so also for people who don't know how to code. So Panda 0 and scikit-0 for people who don't know how to code. They're almost fully available in English. So Panda 0 is being translated, but you already have a lot of material in English. Scikit-0 is being built from scratch in English, and later it will be translated to Brazilian. And there are other things that I teach which are related to Python, computational thinking, problem solving, and programming languages. But these are available in Portuguese. So if you're interested, Python 0 is for starting on Python. Computational thinking is for here it says Blockly, but now it's not only Blockly. You can use the exercises for anything. So now I'm starting people on Python, and then some exercises on problem solving using computational thinking, and then a bit more advanced using abstract data types to solve these problems. Okay, well, let's focus here on the topic today, which is machine learning. The talk's going to be a bit dense, right? So this is scikit-0. There's a little readme here, and it's saying follow this link if you want to access the English version. And it's basically this idea: machine learning before coding. There's a little disclaimer here, something about graphical user interface tools or command line interface tools. We're using something, a bit of both worlds. We're using Google Colab. I'm going to show it to you in a minute. And the idea is that I've already hosted a talk on first steps. I've hosted it in Portuguese and in English, but the English version, the English broadcast was done in an environment where I didn't record what was going on. I wasn't allowed to record at that time. So for that reason, I don't have it here, watch on YouTube badge. I already have a watch on YouTube badge for these, for data preparation using scikit-learn, which was the topic of the last broadcast. And today we'll be talking about data preparation in terms of encoding and transformations, okay? So when we finish, we're gonna have a badge here, watch on YouTube for this one. And so you just click here in open in Colab and it will open it for you. I'm gonna close it now because I already have it in a separate window here. And I'm actually editing this data encoding. Yeah, let's leave it as data transformation. I can go back to this later. So I fixed one line here that was unnecessary and I hadn't realized. So when I was going over the material just before the live, I changed it. Don't worry, I'm gonna upload the new version, but I mean, it's just a line. It doesn't really affect much. And the idea is we were talking about the machine learning pipeline. And the machine learning pipeline has three elements. The first one is data preparation, okay? So before you can do really anything in machine learning, you have to prepare your data. And of course, there's a lot that comes before machine learning. So the machine learning pipeline is one step into the data science process, which starts much, much earlier. So by the time you get to modeling, you know you have data, which is already a lot. That's not something that most people in data science can tell. You know that that data is reasonably adjusted somehow. You're not gonna have to keep collecting data from all over the world and joining them at some point. So some guy did that before, maybe even you, but in a previous stage. And still, you have to prepare your data. Why? Because some of the transformations that we need, they are to machine learning, right? It's things that okay, I think I'm back. I'll be keeping an eye on this to make sure that it's working. So if anything happens, please let me know because the internet connection appears to be a bit unstable today. Yeah, really unstable. That's not nice. I'll try to keep going on and let's see what we can make out of it, okay? So this is pandas. Let's see if the connection improves now, guys. So we're having a bit of technical issues here, but anyway, live streaming goes like that, right? So let's see if you can hear me. Yep, apparently so. If you can give me some feedback saying okay, it's a go, just say, because apparently the connection is coming and going. Anyway, I'm trying my best here. Let's see what we can do. So I was trying to run in pandas here. So let me do this. So I'm gonna run everything and I hope it works, okay? If you don't get data, if you don't get connection, please talk to me in the chat. So we're loading pandas, we're loading Seaborn, right? I've already loaded it, I'll just do it again. And here there's one thing, we're going to use Kaggle. So there's a tutorial here that teaches how to do that. You need to get Kaggle credentials and we're going to upload them, right? So it's uploading. And I'm going to run a cell here that this cell you're not supposed to understand. Yes, so what it was doing is that it was creating some yeah, João Vitor is listening, but the connection is very unstable. Okay, sorry guys, it's something that is escaping me. It's the second time it happens at this time of the day. I'm trying to keep this time of the day because it's supposed to help, but let's see. keep talking and saying if it's a problem, okay? So I've downloaded, so basically I uploaded the credentials and I downloaded the dataset from Kaggle, and trust me, this dataset is going to be a big dataset, right? At least for the purposes we were using before, like for the standards we were using before, it's kind of big. You see how many? Let's see how many features we have. We have 82 features and we have about 3,000 samples, right? Kind of like Iris. Well, let's start isolating the feature we would like to predict. So if we were going all the way to prediction, we would be doing this, okay? I take away sale price and I isolate sale price here, okay? So one comment is that the feature here is real valued, so we call it regression, right? Before we were predicting classes, so we were calling it classification. Here we're predicting a real value, we call it regression, okay? So what kind of things we are going to do here in the beginning? First, I'm going to filter out some features because there's so many features here. It's going to be difficult for us to move on. And don't worry, because we're going to discuss feature selection in the next collab. For this one, I'm going to discard features that are clearly unrelated to the target feature, features that present more than 90% of missing values, and features with low variance. And in terms of categorical features, that means that that most occurring value occurs in more than 90% of the samples. That would be very low variance. Numerical features, the 90% quantile matches the median. Okay, so that is another indication that you don't have much variance there. So of course this could be very premature. I'm not sure I should be discarding so early, but the idea is here I'm trying to keep it reasonable. So if you're talking about 82 features, 81 now because we isolated one, it's still a lot. So let's see how many we can remove from using those criteria. So the ones that are unrelated, the ones that have many features missing, the ones that are nominal and have low variance, the ones that are ordinal and have low variance, the ones that are numerical and have low variance. So I was able to, I'm going to drop a lot, right? That's what I say. Maybe it's premature, we're dropping too many right up front. X shape now 64, so I brought it down from 81 to 64. So I'm doing something that I wouldn't recommend in real life if I were doing this for modeling purposes, but I'm just discussing with you encoding and transformation, right? So we had to make it practical here. So encoding ordinal features. Let me show you the topics here. We're going to be talking about how to encode ordinal features, how to encode nominal features, and how to prepare numerical features, and some of those transformations we can do, and then we wrap it all up, okay? So encoding ordinal features is something that is very important, and very little people talk about it, especially because they don't really separate between what's an ordinal feature and what is a nominal or a numerical feature, right? And they are different, right? So an ordinal feature is a feature, I've pre-processed the data here to understand the features, and I selected which ones are which. So the ordinal features are these ones, right? They either in condition or in quality, and I'm going to show you what they are. Let's isolate them for now. I just want the ordinal features, and see, this is the pattern that I see. And when I was trying to figure out what they meant, it was kind of like this: TA be assessed, PO is poor, GD is good, EX is excellent, FA, I'm not sure, but it's either fantastic or fabulous, right? I don't have a data dictionary here, which is really, really bad, but in the real world, that happens a lot. You need to understand the data, and they don't provide you some dictionary. And there were even some features that I listed as nominal, that like sale condition, they should be probably ordinal, but I don't have a dictionary that helps me understand the ranks. So I've limited this just to these features here, so we could see how to work with them. Since they all follow this pattern, encoding them it's kind of easy, because you can follow this order here, right? I'm going to give it 0 to be assessed, 1 poor, 2 good, 3 excellent, 4 fantastic or fabulous. And we're going to do this using an ordinal encoder from the preprocessing module. And I'm going to give you a list of conditions in the order that I want the data to be encoded. So TA will be position 0, position 1 for poor, position 2 for good, and so on. Okay? So one limitation here is that I want to use this for all of these features, but scikit-learn really forces me into having one list per feature. So I used a trick here from Python to say, please repeat this list as many times as the number of features. Okay? So I have conditions list. If you want to see it here, condition. Oh, well, it's not very practical to see it, but I will try to show it to you. Condition lists. See? Sorry. See now, you're seeing this in horizontal, but the encoder will see this like in vertical, right? Or, I mean, this will be for the first feature, second feature, third feature, and so on. Okay? So I'm going to delete this out for now. Now we can create the encoder saying these are my categories. Okay. And it cannot be, another thing is that it cannot be applied to missing values. So what we're going to do is that we're going to impute TA to be assessed to missing values, which makes a lot of sense, right? So if they had that information, they didn't provide you, so either they didn't access it or they didn't provide it for you. We're going to consider that it's the same. So the simple imputer, we've discussed this in the previous broadcast. It has a strategy called constant, and you can provide this fill value. So fill all the missing values with TA. Now I can make a pipeline, like we've discussed in previous broadcasts. The pipeline will be the imputer and then the encoder. This is my ordinal pipeline. Okay. Pipelines use fit transform rather than fit predict because they're not predicting anything, they're just transforming. And look what I've got now. See, a bunch of numbers. And what do these numbers mean? 0 should be for to be assessed, right? Let's go back here. You see, all these ones are zeros. For basement condition, sample 1 has GD, like good. And for heating, I'm not so sure where QC is. It means fabulous or fantastic, right? So this should be 2, this should be 4. Let's see if they are. Yes, this is 2, this is 4. You see? I was able to encode these data in a way that now they are numerical. And this is really important because when you read about categorical feature encoding, people are always talking about one-hot encoding, which is what we're going to discuss next. But it's very different because what we really need to do here is that we want to tell the algorithm that there's an order here, that good is better than poor, that excellent is better than good. And this is very important. And of course we could just encode this as like treat this as a numerical feature by just replacing all the values, and in a sense this is what we're doing. But you see that there's an ordinal encoder that is specific for this kind of transformation. It's exactly because these are ordinal features, okay? Now let's go to nominal features, which are features that are also categorical, but they don't have an order. And I've discussed one-hot encoding. This is what we're going to do. So just for you to see, all these features, I'm considering them to be nominal. You see that, let's see, garage finish, for sure there's a rank here, like finish and unfinished. There's another category, but I don't really know how to rank them. Not because of finished and unfinished, for sure. Finish is better than unfinished, but there were some other categories I could not understand how to rank. And there were other things here like this. So a data dictionary here really makes a difference, right? Let's check one nominal feature to understand what one-hot encoding does. So we're going to do this. Let's see, lot shape has regular, IR1, IR2, IR3. Okay? So what we're going to do is that these 4 possibilities here, these 4 values, are going to be replaced. So this feature had 4 values. So that feature is going to become now 4 features. Each feature is binary. So the first feature refers to this, the second feature refers to this, the third feature refers to this, and the fourth feature refers to this. So if the sample presented the value regular, the only binary feature that's going to be active is the one that corresponds to regular. Let's see how it works. So I'm going to make the column transformer. We've discussed this on the previous broadcast. I'm going to use a one-hot encoder applied to lot shape. One-hot encoder, by default, it creates a sparse matrix because it's much more space efficient. But here I'm trying to keep things simple. I'm gonna say please don't do that. I want to keep understanding what's going on. So now I'm gonna fit transform the data, and then I'm gonna wrap the output as a data frame, right? And since it creates a lot of features, we're gonna use the method from nominal encoder called getFeatureNames, which basically will give us the name of the features that were created, right? And then we can see what's going on. So see here, one hot encoder, x0 stands for feature 0, right? So there was only one feature, it's called feature 0, x0. IR1, you see, now for IR2, IR3, IR, and here it's regular, right? So for each line, we can only have one of these binary features active, because that was the category that was present in the original sample. So for the first sample, it was IR1, for the second sample, it was regular, for the third, it was IR1, for the fourth, it was regular, and so on and so forth, right? So that's really scary. I mean, I didn't use that before. And when I started studying on machine learning and Python and scikit-learn and this stuff, and I saw how categorical features were treated, I really got scared. Honestly, I really got scared. Because basically, you start exploding the number of features that you have. And we were talking about, we already had 64, I guess. Let me just go back a bit. We had 64 features. And out of those 64 features, we have all the nominal ones. I didn't see the shape here, but let's see the shape. X nominal, that shape. We have 21 features. So it's very easy that these will become 80 features. Let's see what's going to happen, right? Let's apply it so you can see. Sorry, let me go back to where we were. We were here. So I'm going to apply this. The idea is I'm going to use an imputer, like replace the value with the most frequent one. Whatever is the most frequent for that category, please use it. And then apply the one hot encoder. Then I'm going to say fit transform the data. By the way, so this is something I should have done here. Sparse equals false. So I can remove this. Okay. And what's going to happen is this. I want to get the data names. And it's a bit tricky. I didn't go into the details here, but basically it's like the pipeline has steps, right? So the steps in the pipeline are the imputer and the encoder, and I want to access the encoder. And the encoder has two elements, which is the features it's going to be applied to and the actual encoder. I think that's it. And so I'm getting the second value, and from that I'm saying get feature names. Okay? Let's see what happens here. Ooh. And when I say get feature names, I can give the name of the original feature so it replaces, okay? So you can dive a bit into this to understand better what was going on. But let's see here. So there was a feature called MS zoning, and it had 5, 6, oh my god, so many values. 1, 2, 3, 4, 5, 6, 7. 7 possible values. It became 7 features. There was something here called lot shape. We saw it before. It had 4 possibilities. They're here. There was something called land contour. It had 4 possible values. They're here. So I was expecting that in average, each categorical feature would have 4 possibilities, right? So that should have transformed data into about 80 features. But here we have 165 features. They're all binary, okay, but still it's a lot. I didn't really go to check what kind of things it is, but you see here, for instance, here's the neighborhood, for instance. The neighborhood has all these possible values to the point that it's being summarized. Oh my god, it's so many things. So this is something I could have gone back here and say, okay, so I don't want the neighborhood to be encoded like this. But the problem is, you really think that if you're trying to predict sales price, let's say your price, that the neighborhood doesn't matter? Sure it does. What we could have done here, if you wanted to make it a bit simpler, is to cluster these neighborhoods and say, so these are neighborhoods that I know, they're expensive. These are like high-end. These are a bit cheaper, and these are really, really cheap. And then I would have 3 categories instead of all of those, okay? So this is an example of some things that you probably need to do when you're dealing with categorical features. I'm going to take a break now so that you can provide your questions, because this was discussing categorical features. We talked about ordinal and nominal, and then I'm going to move on to numerical features, which is a whole different universe. So it's the best time I can think of to say, okay, can you please provide some feedback, some questions, and I'm available and I'm listening. There's like a 15 to 20 seconds delay between what I say and when you read it. So you can provide some questions and I'll be waiting. If I don't see your message because it came very late, don't worry. When I come back here, I'm going to try to answer, okay? Sorry. Well, I don't see any questions, but as I said, if you want to provide questions, don't worry. I'm going to be coming back here to see them. So I'm going to move on to the numerical part, okay? So let's talk about, talk about numerical features, okay? And the idea is that when we're talking about numerical features, we're not talking about encoding because, well, they're numbers already, and that's the kind of feature that that scikit-learn already expects, right? But what we want here is to see about the scale and about the scale and the distribution of the data. Okay, so let's talk about scale first. Okay, sorry, there's a question. So there's a question here from João Vito. I think the stream jumped around a bit when you were explaining this, so I didn't get it. But what's really the difference between have one hot encoding on all the features versus doing the one hot encoding on the clusters of a specific feature? So basically it's the number of binary features that you get, that you start increasing so many features that, I mean, for machine learning algorithms, make sense. Yeah. So what's the difference? Yeah, you're already coming that up front. So what's the difference for the final model? I would say that there's one issue we're going to discuss later, which is called the dimensionality curse, which is that when you scale the number of dimensions too much, you start having problems for the algorithms, right? So if you're introducing too many dimensions, like we're doing here, you're kind of like doing something against the performance of your algorithm. So it's always better. I mean, usually what you do is that you prepare all these features, and then in the next step you're going to be doing some selection or some extraction to bring those features back to a more reasonable level, right, to a more reasonable number. So that's one of the reasons why you should be careful when you prepare so many categorical, I mean, when you apply on one hot encoding and you end up with so many binary features, right? Because anyway, this is a problem that is always about dimensionality, right? So if you had a problem that had only 2 dimensions, only 2 features, either it's going to be not enough information to split the data, or very easy to split the data because you can understand what's going on, right? So we're always trying to keep this in balance. So going back to feature scaling, I hope you answered I answered your questions, but you can send some comments. So as soon as I see them, I'll discuss them. So let's isolate here the numerical features. We have some numerical features, again, I think just about the same number of numerical features, and we had like 21 for nominal. We have 35 for numerical, right? So, oh, I rewrote those already here. Great. So the first thing we can try to do is we talk about fitting the scale of the data to a range, to a common range, right? So let's see three different features here: overall quality, year built, and I never know, but I think this is ground living area. Okay, so without a data dictionary, I'm trying to understand this. I think it's ground living area. So if you see here, the mean values for these features are very different, like 1, 300, and 1800. If you see the maximum value, 10, 2000, and 5600. So you can see that these features, they have very different scales. Now, if you're talking about predictors or estimators that depend on the absolute distance between the things, between the features, this is going to be a problem. Of course, it can come in your favor if like the largest values or the ranges here are in favor of the features that really matter the most. But in principle, you should not trust on that, right? You should give them all in a uniform way, and then the algorithm should be able to identify which one is the best. We're going to use min-max scalar for this, and then we can apply min-max, fit, transform. I'm wrapping the output as a data frame always because I want to keep understanding my data. So machine learning in scikit-learn is a pipeline. You start from something that you understand, you end up from a result, right? And in between, all the transformations are considering that you lose the capability of understanding the data, right? And this is very bad. But I understand them because they're trying to be efficient. And being efficient means using very low-level data structures like the arrays from NumPy. But here, I'm going to always be bringing you back to data frames so we can see what's going on, right? Now see, I applied the min-max scalar. All the values were transformed. And let's see what that did to the features we had before. See, maximum value of 1 for everybody, minimal value of 0 for everybody, and everybody in between has been transformed. So the transformation is exactly this, like the maximum value will be 1 and the minimum value will be 0. So what it does is that first I subtract that previous minimal value from everybody to make sure that the minimum value is at 0. And then I subtract the new maximum value, I divide every value, every transformed value by the new transformed maximum value so that the maximum value will be 1. So that's a transformation basically. It just shifts the data to start at 0 and then scales it down to be between 0 and 1. That's called scaling the data to fit a range. And we could also center the data. And centering the data means that the data will have 0 mean, right? So the mean of the data will be exactly at 0. There's a formula for this definition. Here we're applying it as the standard scalar. And generally when you use the standard scalar, it does two things at the same time. Here I'm going to do it stepwisely. So first I'm just going to center the data. So I'm saying, oh, please don't touch the standard deviation, okay? So fit transform, the same idea from before. Now if I describe those features again, you see that I lost the minimum and maximum thing. You cannot have both things. But now the mean is at 0 for everybody. No, that's not 0. Yeah, that's 0. Computers have a lot of difficult when you're talking about floating point values and like real valued features. So that's as fast as it can to represent a 0. It means that for all purposes that's going to be considered a 0, right? And to be honest, not all purposes. I've had problems and significant issues because of this. So what I would do is, if I really wanted to make sure this happens, and I could say, oh, please change the mean for 0, I would do it. But I cannot, so anyway. And then the last thing is to scale the variance so that the variance equals 1. And we do that, again, with standard scalar. This time I say, don't touch the mean. So it's going to only touch the standard deviation. And let me show you the variance here. The variance here went to 1, or as close to it as it could. And the standard deviation by default also went to 1, right? Since the standard deviation is the square root of the variance. Well, why did I have to do this stepwisely? Because I wanted to discuss them step by step. But you can see that standardization is something that is usually done as a whole, right? At the same time, you center the data and you scale the variance to a unit, okay? There are other kind of transformations you can do with numerical values. For instance, you can transform it in an ordinal feature. So what you do is that you ask all the values to be cut into intervals, usually intervals of fixed size. That's a possibility. And then you're saying, okay, if I have three intervals, I would say low, medium, and high. And that's my new ordinal feature. And then I can encode that ordinal feature as just 0, 1, and 2. Okay? So this is one of the things you can do. It's another, I didn't talk about discretization here, but this is possible. The other thing you could do is what some people call it normalization, which be to say that it has a unit norm. I didn't go into these details, but the idea is that you have so many possibilities here. Discretization should be here, but it was so long already that I thought, okay, maybe it's better that I don't show it now. Let me see what happens with the notebook as I'm presenting, and later I can bring it up, right? So that's the only thing I think is really worth mentioning, because sometimes it will save you. Also, sometimes you don't discretize from the original scale, you discretize from a log transform scale, basically because the interval is too big. Anyway, I'm going to show this using pipelines. So I'm going to apply an imputer first. So I'm going to use KNN imputer from the previous broadcast, then a min-max scaler and a standard scaler, right? And then my numerical features should be ready. So let's do this, and let's see what happens here. Well, I don't really have much control of what happened, but I could have plotted this for you to see, but describing for me made more sense, just so that the mean is at 0. Wait, the mean is not at 0 anymore because of the imprecision. Again, it's the same, right? This is still 0 for all purposes that we consider. And the variance is also at 0, at 1, sorry. What doesn't happen is that the scales min and max are not at 0 and 1, okay? Basically because there's no way you can do all the things at the same time. But that's why I say, first I applied the range fitting procedure to make sure that when I applied the mean and the standardization, it would be applying to ranges that were the same, okay? Now, we could talk about distributions. So here you were shifting, we're doing a lot of things, but I mean, the distribution shape is not changing, at least not from one type of distribution to another. And let's say this is these many methods that we discussed in Panda 0 about testing if the data matches the normal distribution. Here it's a bit verbose, a bit polluted, but if we just check for the second one, we want to find values that are above 0.05. If we find values that are above 0.05, that's an indication that that feature follows a normal distribution, okay? Because the test is checking if it doesn't follow a normal distribution, and it's sure that it doesn't follow a normal distribution if the value is below 0.05. So for our purposes here, we're looking for above 0.05 to say, yep, so I'm sure that this one, they couldn't prove that it follows, that it doesn't follow a normal distribution, so I accept that it follows. Okay. Well, that's not the case for anything here, but everything in statistics and machine learning is sweeter and easier if you're talking about normal distributions. So there are some transformations you can try. We've talked before about log transformations, right, which are very simple. There are a bit more elaborate approaches like quantile transformation. So this was discussed already in Panda 0 when we're talking about QQ plots. So you use this idea of quantization, which is basically replacing each value for the quantile it belongs to. And the idea is that this transformation should help you bring it closer to a different distribution, in this case a normal distribution. Let's see if it works. I'm going to apply this. So KNN imputer, min-max scaler, standard scaler, and finally the quantile transformer, trying to bring it to a normal distribution. Here are my features. And when I apply the normal test, bam, the only one that made, for which it was able to bring closer was year sold. For all the others it couldn't. Well, the values changed. You can even see that many now are actually 0, so they're coming a bit closer, but that's not enough. There are other approaches called like power transformations. I just showed one here for you to see. It's kind of like a logarithm transformation, but it's a bit more elaborate. So let's see how it works. You see that it even takes a bit more time to run. And come on. Why is it taking so long? I didn't remember it taking this long. Well, in the meantime, if you have questions, I'm not sure if it's taking very long because my connection dropped. Nope. Okay, it's here. And now if I apply the normal test to everybody, I see 1, 2, 3, 4 features that now apparently follow a normal distribution. Ear-sewed does not. So different transformations will affect different features in different ways. Okay. So I want to wrap it all, but first I also want to get feedback from you on this part about transforming numerical data. So please bring me as many questions as you can. And as I said, there's a bit of a delay here. I'm gonna sit down and drink water while you listen to what I'm saying. Okay, if you have questions, you can write them down. As soon as I see them, I'm gonna come back to them, okay? So let's wrap everything up. The idea is I was isolating the features, but I don't need to do that. I can do them all at the same time. So I can say, please apply ordinal pipe to ordinal, nominal pipe to nominal, numerical pipe to numerical, okay? This will be my full pipeline. Now there's one trick here. I told you I want to keep the understanding what the features mean, and I'll have to fit the nominal pipe by myself outside so I can get features. Okay, wait. I usually see people using either standard scalar or min-max when transforming the data. Never the two at the same time like I saw in your pipeline. Is there any particular reason to do that? To be honest, the idea is that all these transformations are something that should be done heuristically, right? So my impression is that the more I study about data preparation, about feature engineering, about everything there is to do with machine learning, I get more and more convinced of the importance of the research field I work on, which is automated engineering, in this case automated machine learning. And I convinced myself of how complex it is to formulate like all the possibilities that you have at hand when you're dealing with data, right? So we have this joke that people with a lot of gray hair for sure know how to do this, but it costs a lot. It takes a while for you to have this kind of experience. So I've studied a lot my field, which is heuristic optimization. And if you ask me things like, for instance, here, like transforming things, ordinal features, when people usually don't, I would say do that. It makes a difference. Or this idea of keeping the number of binary features constrained. Please do be careful about that. That's something I already learned from experience. Now, about min-max, standard scalar, and these kind of things. In heuristic optimization, min-max is very used. Standard scalar is not. In machine learning, standard scalar is more used, min-max is not so much. So that's what I'm saying. I mean, maybe people with gray hair, with a lot of gray hair, will tell you best. But for me, the idea is you have many possibilities here, and the best way to go is to go for AutoML. But anyway, that's my opinion. I can even bring some examples. We do some AutoML work on images, and people usually think that for image computer vision feature extraction we do a better job than feature selection. And for some reason, feature selection is always getting selected on our pipelines, which still do reasonably well. Maybe it's the available options for feature extraction that were not good enough, but still, it's the options that people usually try. And another thing was that you would expect that the sorry, I forgot exactly what I was going to say. When I remember the other example, I'll bring it back to you. Okay, but the idea is this: you're not always going to see in advance what to do. So experimenting is a big part here. So that's why I think heuristic selection of components for the pipelines. I mean, my PhD was on that, so I will always advocate for that. Anyway, I hope I've provided you an idea that sometimes you have an option, sometimes use the other. Hope I helped you. So here I want to get the feature names for like the nominal features, so I had to fit it outside because whatever happens here is like it happens at once, so I don't get to access the model. So I ran this outside, and my column names will be the ordinal features, then the transform nominal features, which I got from here, and the numerical features. Okay, combine all of them, concatenate all of them, and now I can say, please apply the fit transform to X, wrap it in a data frame, and remember these column names because I want to understand what's going on. And here they are. So all the ordinal features are here that I transformed in the beginning. All the nominal features are here. At some point there are going to be ellipses here, yeah. And then the rest of the nominal features, and all of the numerical features, at some point there should be ellipses. Nope. I don't know why there are ellipses here and not in there. Later I'm going to try to figure it out. But you see, now the whole thing was transformed from a single pipeline, but we would never have reached this single pipeline if we hadn't built the smaller pipelines before. So with the idea of column transformers, this gets even more difficult because, of course, different columns could probably be dealt with and transformed by different transformations and for different models. So it's a complex equation. It depends on the feature. It depends on the algorithm you're talking about. It depends on the metric. It depends on the setup that you have, like how much time you can give for a model to be evaluated. I remember the second example from the AutoML project. K and N got selected so many times for computer vision that I really lost count. And say, dude, but K and N is a very, very simple estimator. Yep, but it was getting good results. So that's the point, right? So it depends on so many factors that in heuristic optimization, we don't consider that you can do these things manually. Some people do, and their papers get rejected. In machine learning, this is becoming more and more a common sense in the field. Like you submit to a great conference, they're always going to ask, how did you do this? How did you configure this? Did you test for hyperparameters and stuff? And we're going to discuss this in the future. I hope you see that this is something that is very complex. And in the end, you can get someone that is just an expert and has a lot of experience, and you say, do this, and this, and it works. And it delivers, and that's it. I do that in heuristic optimization. Some guy asks me, I have this problem, I would like to see a simple solution for that. I say, take this, and this, and it works. Because I have enough experience in that field to say that. But I always tell him, this gives you a starting point. There are many other things you could try that probably could even get you even better results, right? So it's like, let's say, fashion MNIST. MNIST. MNIST is a computer vision problem for which people use it to get 97%. They were thinking this was awesome because 97%, man, it's a lot of accuracy, right? For classification, it is. And then people kept working on it and started saying, dude, but almost everybody gets 97%. So 97% doesn't mean much. Let's raise up the bar a bit. And then they started discussing 99.9, 99.7, 99.97. So it's all about where you want to go. And that depends on the application domain you're talking about, on the business you're talking about, because for that business, 0.5% can mean a lot, or 0.5% can mean nothing. If it means nothing, provide a solution that is enough. I'll give you an example now with COVID. The test that the Brazilian government is using has a sensitivity of 40%, which is very, very low. But they're looking at that and say, dude, this will provide me an answer very quickly. And this can be used at scale. So 40% is acceptable. So it all goes with the application domain, with the business field you're talking about. Okay. Well, I'm really happy about this broadcast, even if it had a lot of technical challenges. But it really took me a while to prepare this notebook. But I think it got very, very concise in the most important ideas I would like to discuss, except for discretization. But please provide me feedback if you will. If you have any questions, I'm here. We have 53 minutes of broadcast. The idea is to go up to 1 hour, so I have enough time to be here. If you don't, no problem. Just say bye-bye, see you next time, and have a nice weekend. Remember, next week is the same thing, Mondays and Wednesdays at 8:30 in Portuguese, problem solving and computational thinking. Tuesdays and Thursdays at 5 UTC time, 8 o'clock UTC time. It's the broadcast on machine learning and data science. Data science on Tuesdays with pandas, machine learning on Thursdays with scikit. Yeah, João Vitor, now I'm looking forward to an introduction to AllML. There is already a tutorial if you want to see. If you look at my GitHub, there is one code. Oh, sorry, let me find it here. So if you look at my GitHub, I gave a talk on this at Python Brazil, like the PyCon in Brazil. And it's available there. Let me just see if I can find it. Yeah, so the internet connection is not helping a lot. Gateway timeout. Oh, I didn't even know this existed. Is GitHub down or is it me? Let's check. GitHub is down. Oh my god. Well, anyway, that's the best I could do. But if you go to my GitHub, you're gonna find there. You Google for AutoML in my GitHub, you're gonna see something. And on YouTube, you find the talk too. I don't know if I linked the talk there. And also I should add to my channel. That's a great idea. I'll add it as soon as I can. But the idea is Python Brazil, AutoML. It should show me, yep, AutoML with Python, machine learning made easy-ish. So you can see a bit here, and you can also see on GitHub, because it's not in the description here, but the GitHub is that. Okay. Well, thank you for being there, guys, and see you next time. Okay.